Chapter 9 Parametric and Non-parametric Test of Independence. In the previous chapter, we conducted hypothesis test on the population mean and the population variance. Here we conduct hypothesis test concerning the population correlation. We will look at the parametric approach as well as the non-parametric approach. Then we look at the test of independence using the contingency table data. In the previous chapter, we have conducted tests concerning various population parameters like the population mean and the population variance. In this chapter, we will be conducting tests concerning the population correlation, the correlation between two variables. In many investment contexts, we are interested in assessing the strength of the relationship between two variables. We want to find out how strongly two variables are related to each other. So we evaluate this strength of relationship using correlation. Correlation measures the strength of linear relationship between the two variables. So in this chapter, we will be conducting hypothesis test concerning the population correlation using the correlation of a sample data. We will have two different tests conducted around the population correlation. One is the parametric test of correlation and the second is non-parametric test of correlation. Let us start with the parametric test of a correlation. Here we want to test the correlation between two variables, and the test statistic that we use is this, where the test statistic equals to the sample correlation multiplied by the root of sample size minus 2 divided by root of 1 minus the sample correlation squared. And the test statistic follows a t distribution, and this is the degree of freedom that we will use to find out the critical value using a t distribution table. Here it is assumed that the population data of the two variables follow a normal distribution. That's why it is referred to as the parametric test. And based on that assumption that the two population data follows a normal distribution, we are able to use this statistic. But if the population data don't follow normal distribution, they deviate from normal distribution, then the conclusion that we get using this test statistic and this distribution might be incorrect. And the formula of sample correlation is the sample covariance divided by the sample standard deviation of variable x multiplied by the sample standard deviation of variable y. We have seen this formula many times in the previous chapters. So we conduct the hypothesis test on the population correlation, which is represented by rho. We conduct the hypothesis test based on the correlation coefficient of the sample data. We also refer to this correlation coefficient of the sample data as parametric correlation or Pearson's correlation or bivariate correlation and is denoted by small r. The magnitude of the correlation from the sample data required to reject the null hypothesis decreases as the sample size increases. So as the sample size increases, the magnitude of R which is required to reject the null hypothesis decreases. This is because of two reasons. As the sample size increases, the absolute value of the numerator increases, resulting in a larger t-stat. So if you look at the formula of test statistic, the increase in sample size, the numerator also increases. So our t-stat becomes larger. So when the t-stat becomes larger, the probability of rejecting the null hypothesis also increases. So suppose this is the t distribution of the test statistic. These are the critical values. So as the test statistic increases, the absolute value of the test statistic increases. It means that the test statistic now lies in the extreme regions, in the rejection regions. So when the sample size increases, we can reject the null hypothesis even if we have a small sample correlation. So this is the first reason. The second reason is, as the sample size increases, the degrees of freedom increases. So the absolute critical values decrease. So the degree of freedom is n minus 2. So as the sample size increases, so does the degree of freedom. When that happens, the critical values decrease. So with a higher sample size, say the critical value now comes closer. That is, the rejection region is now larger. So there is a higher possibility of rejecting the null hypothesis when the sample size increases, even if the sample correlation is low. So with this, we can conclude two things: that the significance is achieved at a faster rate with a higher sample size. Significance refers to the population correlation being significantly different from 0. So with a higher sample size, the population correlation being significant from 0, being significantly different from 0, is achieved at a faster rate. And the second conclusion that we can draw is, the power of test increases with the higher sample size. If you remember, power of test refers to rejecting a false null hypothesis. So as the sample size increases, the probability of rejecting a null hypothesis increases. So does the probability of rejecting a false null hypothesis also increases. But the type 1 error also increases, which is to reject the true null hypothesis. Let us solve the following example. An analyst is examining the annual returns for investment 1 and investment 2 over 33 years. So this is the exhibit of the returns of two investment. Although this time series provides some useful information, the analyst is most interested in quantifying how the returns of these two series are related. So she calculates the correlation coefficient, which is equals to 0.43051. So the sample size is 33 years and the sample correlation equals to 0.43051. The question is there a significant positive correlation between these two return series if she uses a 1% level of significance? The question is there a significant positive correlation? Meaning, the analyst wants to know whether the correlation is greater than 0. So the hypothesis will be, alternative hypothesis is correlation greater than 0, and the null hypothesis will be correlation less than or equal to 0. So this is a right-tailed test. If instead of positive, if it was negative, then this would have been a left-tailed test. And if analyst had no belief as to whether it was positive or negative, if she only believed that the population correlation is significant, then that would have been a two-tailed test. So let us find out the t statistic first. T stat equals to sample correlation, which is 0.43051 multiplied by n minus 2, which is 31, divided by root of 1 minus 0.43051 squared. So the t stat is 2.6558. Now let us find out the critical value. We need to look into the t distribution table. The degree of freedom is 31 and the level of significance is 1%, 1% on the right side. So this is the t distribution table. So we are concerned with a 1% level of significance. That is, we are concerned with this column, and degree of freedom is 31. So the concerned critical value is 2.453 and our t statistic is 2.6558. So it lies in the rejection region. So we can say that we reject the null hypothesis and conclude that there is a significant positive correlation between two investment. Now suppose instead of a right-tailed test, if it was a left-tailed test and we still had 1% level of significance, then we would still use the same distribution table we will still use this column and this row. And instead of positive 2.453, we would have had negative 2.453. So for right tailed as well as left tailed, we use the same distribution table. So I want you to solve this question by yourself, where we have the sample correlation of the funds with each other as well as the correlation of each of the funds with the S&P 500. So in total we have 10 sample correlation, and you need to test whether these correlation are significant from 0 or not. You will be using a 5% level of significance, and the critical value is plus or minus 2.032. So if you have solved the question, then this is the test statistic for each of the correlations. So of the 10 correlations, 9 correlation appears to be significant. Only the correlation between fund 3 and fund 4 appears to be insignificant, appears to be closer to 0. So we accept the null hypothesis for fund 3 and fund 4's correlation, and we reject the null hypothesis for all the remaining 9 correlations. Previously, while conducting the hypothesis test concerning the correlation, we assumed that the population of the two variables followed a normal distribution. That's why we used the parametric test of correlation. But what if the population of two variables deviates significantly from the normal distribution? Then we conduct a non-parametric test of the correlation. So here we want to conduct the hypothesis test concerning the correlation between two variables, where the population data of the two variables deviates significantly from the normal distribution. The test statistic that we used in the parametric test is also used here, but the difference lies in the correlation that we used. In the previous test that we conducted, we used the Pearson correlation coefficient, or we also call it as the parametric correlation. Here we conduct the hypothesis test using the Spearman rank correlation coefficient, and we represent this by R subscript S. And this is the formula of the Spearman rank correlation coefficient. As you can see, this formula is very different from the formula of sample correlation we have seen earlier. So in a while, we will look at this correlation coefficient in detail. So the test statistic here also follows a t distribution, and this is the degree of freedom we use to compute the critical value. So the only difference between the parametric and the non-parametric test is the use of the correlation. Everything else, the process still remains the same. So after computing the test statistic, we use the t distribution table to compute the critical value based on the degree of freedom and the level of significance specified. Now let us look at an example to see how do we calculate the Spearman rank correlation coefficient. The Spearman rank correlation is calculated based on the ranks of the each observation within their sample. So for example, we have two funds, Fund A and Fund B. We have collected the annual returns for the past 35 years. So our sample size is 35, and we have 35 annual returns for all the 35 years. So first let us see how do we calculate the parametric correlation, or simply the sample correlation that we used to calculate. So first we calculate the deviation of each observation from their sample mean. We do it for both the funds, for Fund A as well as Fund B. So we have 35 such deviation for each of the fund. Then we multiply each of this deviation. Say this is deviation 1 and this is deviation 2. We multiply deviation 1 by deviation 2, and we have 35 deviation products. We add all these deviation products and we divide it by n minus 1. This is the covariance, or this is the sample covariance that we get, and we divide this by, and we divide the sample covariance by sample standard deviation of each variable. So this is how we use to calculate the sample correlation coefficient. But in a Spearman rank correlation, what we do is We first rank each observation within their own sample. Rank 1 implies that it is the largest observation and rank 35 implies that it is the smallest observation. So for observation 1, which is 2.453, it has a rank of 27 within its own sample. Similarly, the 33rd observation, which is 7.3, has a rank of 5 within its sample. We also rank each observation of fund B, and these are the ranks. After calculating the ranks of each fund, we find the difference of the ranks. So we take 27 minus 31, we get -4. Similarly, we get 35 such differences. We square the differences and this is the difference squared that we have. And we take sum of all the difference squared. So the Spearman rank correlation coefficient equals to 1 minus 6 multiplied by the sum of the difference squared, which is 2202, and dividing it by the sample size multiplied by sample size squared minus 1. So the Spearman rank correlation coefficient comes out to be 0.6916. So we insert this correlation coefficient in the test statistic. We find out the test statistic and then we compare this test statistic with the critical values computed and then conclude whether we want to accept or reject the null hypothesis. The process remains the same except for the calculation of the sample correlation coefficient. So suppose in fund A, we have two observations. Both the observations are same and the rank of these observations are 16 and 17. So when we have two observations which are same, instead of ranking them different ranks, what we do is we take average of the ranks. So we get 16.5 and we assign 16.5 to both the observation. So if more than one observations are tied, then we assign the average of the ranks to each observation. Let us look at the following example. You are interested in whether the excess risk adjusted return, called as the alpha, whether the alpha is correlated with the mutual fund expense ratio for the US large cap growth fund. So we have a sample size of 9 and we have the data of alpha and the expense ratio. Determine whether to reject the null hypothesis at a 5% level of significance, and the critical values at this level of significance is 2.306. So because they have already given that, we have two critical values, one for the right side and one for the left side, which implies that we are conducting a two-tailed test. So the hypothesis will be, null hypothesis is correlation between alpha and expense ratio is 0, and the alternative hypothesis is correlation between them is not equal to 0. So before finding out the test statistic, let us find out the Spearman rank correlation coefficient. So on the exam, you won't be asked to perform such lengthy calculations. Either you will be directly given with the difference squared or you will be given with the ranks of each of the variable from which you need to calculate the difference squared, the sum of the difference squared. So in this case, the sum of the difference squared is 144.5. So the Spearman rank correlation coefficient equals to 1 minus 6 multiplied by the sum of difference squared, which is 144.5, divided by the sample size of 9 multiplied by sample size squared minus 1. So the Spearman rank correlation coefficient is negative 0.20416 and the T-stat equals to Spearman rank correlation coefficient multiplied by n minus 2 divided by root of 1 minus r squared. So the T-stat comes out to be negative 0.5117. So because it's a two-tailed test, we have negative 2.306 and positive 2.306 as critical values. And the T-stat lies somewhere over here, which is in the acceptance region. So we accept or we fail to reject the null hypothesis. So we conclude that the correlation between the two is 0. They both are not correlated to each other. I want you to solve this example by yourself, where you are given the Spearman rank correlation between various exchange rate. So these are the Spearman rank correlation coefficient. So the question is, for any of this pairwise Spearman rank correlation, can we reject the null hypothesis of no correlation at the 5% level of significance? So this is a two-tailed test where the null hypothesis is that there is no correlation between the currencies. The alternative hypothesis is that there is correlation between the currency pairs. You need to calculate the test statistic for each of the currency pairs correlation and compare it with the critical value. So the critical value at 5% level of significance is plus minus 1.97338. So these are the test statistic for each of the currency pair. Compare each of the test statistic with the critical value and decide for each currency pair whether they are correlated or not. Until now, we have conducted the hypothesis test of correlation between two variables. Now let us see how do we conduct the hypothesis test of independence between two variables when the variables are categorical or discrete. Although independence and correlation are technically different, but as of now consider them as one and the same for ease of illustration purpose. So here we want to test whether two variables which are categorical or discrete, whether they are independent of each other or not. Definitely, when two variables are categorical or discrete, we cannot use the correlation to assess the relationship between these two variables. Hence, we also cannot use the hypothesis testing method that we have seen earlier to find out whether these two variables are independent or not. So for example, if I want to find out the correlation between the market cap and the revenue of a company. So suppose in my sample I have 10 companies, where the first company has say a market cap of $1,000 billion. The second company has a market cap of $150 billion and so on. And the revenue is say $20 billion, $1.1 billion and so on. Because both are in numerical terms, it becomes easy to find out the correlation between the two variables. Therefore, we can use the hypothesis testing method we have seen previously to conduct the test on the population correlation. But what if I want to check whether the market cap and the investment type, whether any relationship exists between them or not? Suppose I have 10 companies in the sample, where say the first company has a market cap of $1,000 billion, second company has a market cap of $150 billion. And suppose I classify the first company as a growth company and I classify the second company as a value company. Similarly, I classify all the 10 companies. Now, because the investment type is a categorical data, it becomes difficult to find whether these two variables are related or not. Hence, correlation cannot be used in such cases. In categorical variable, each value is a category or is a qualitative attribute. And in such case, we can perform the test of independence using a non-parametric test statistic. So here we want to test the independence between two variables when the variables are categorical. This is the test statistic that we use, where this M refers to the number of rows multiplied by number of columns, that is total number of cell in the table, and the OIJ refers to the observed frequency in row I and column J, and EIJ refers to the expected frequency in row I and column J. This test statistic follows a chi-squared distribution. Degree of freedom that will be used to find the critical value is number of row minus 1 multiplied by number of column minus 1. So the chances of getting tested on the calculation is pretty low, but still we will look at an example so that you have basic understanding of how do we conduct the test of independence? Here it is always a right-tailed test. When we want to conduct a hypothesis test of independence between two variables which are categorical, it is always a right-tailed test, and the two hypotheses are as follows. The null hypothesis states that the two variables are not related, that is, they are independent of each other. Whereas alternative hypothesis states the two variables are related, they are dependent on each other. So if the test statistic that we have calculated, say, falls to the right of the critical value, then we reject the null hypothesis. But if the test statistic falls to the left of the critical value, then we accept the null hypothesis. Let us solve the following example. We observe following 1594 exchange traded fund based on two classification, the size and the investment type. We are required to perform the test of independence between size and investment type. So this is what we refer to as the contingency table or a two-way table. So we have three investment type, value, growth and blend, and we have three different sizes, small, medium and large. And in total we have 1594 observation. And these are the respective number of ETFs in each investment type. So these are the respective number of ETFs in each size. And we refer to each of these as cells. In this case we have 9 such cells, where the first cell here represents that number of ETFs which have small size and which have value investment type. Similarly, 202 represents number of ETFs which are large as well as which have growth investment type. So let us state the hypothesis first and then we calculate the test statistic. Now let us calculate the test statistic. The test statistic is chi squared, and to calculate the test statistic we require four things. We need how many number of rows are there in the contingency table, how many columns are there, and the observed frequency in each cell and the expected frequency in each cell. So in this case we have three rows, value, growth and blend. Let's name it as 1, 2 and 3. So we have three rows and we have three columns, small, medium and large. Let's name it as 1, 2 and 3. Now the next thing we need is the observed frequency in each cell, where I refers to the row number and J refers to the column number. So the observed frequency at row 2 and column 3 will be this. The observed frequency at row 2 and column 3 is 202. Similarly, each cell is represented by a row number and a column number. And we will have 9 such observed frequency. The next thing that we need is the expected frequency in each cell. Just like observed frequency, expected frequency are also represented by a row number and a column number. So what is the expected frequency? Expected frequency is the number of frequency that should be there in each cell for the two variables to be completely independent. So for two variables to be completely independent, we need to have certain expected frequency in each cell. So we can say that if the expected frequency which are required for the two variables to be completely independent, if the expected frequency is the same as observed frequency, then we can conclude that both of them are completely independent. But practically speaking, they both will never be the same. There will be some differences between the observed frequency and the expected frequency in each cell. Now how do we calculate the expected frequencies? This is the formula of expected frequency. Suppose we want to calculate the expected frequency at row 2 and column 3. How do we calculate this is, we take the total of row 2, which is 366. We multiply it by total of the column 3, which is 1065. And we divide it by the total number of observations we have, which is 1594. So the expected frequency at this intersection is 244.53. So as you can see, the observed frequency was 202, but the expected frequency is different than the observed frequency. So similarly, we calculate the expected frequency for each cell. So this is the table of the expected frequency at each cell. Just like we had the contingency table which showed the observed frequency at each cell, we also have the expected frequency at each cell. So we required 4 things, which was the number of row, number of column, the observed frequency is stable and the expected frequency is stable. So we have all the 4 things that we require to calculate the test statistic. Now let us see how do we calculate the test statistic. Test statistic chi squared equals to the sum of all the scaled squared deviation. Now what is the scaled squared deviation? We take the observed frequency at each cell, subtract the expected frequency at the particular cell. We take square of this. This is the squared deviation. And when we divide this by the expected frequency at that cell, we refer to this term as the scaled squared deviation. And we will have 9 such scaled squared deviation term, and we will add all the scaled squared deviation term to arrive at our test statistic. So let us calculate the scaled squared deviation term for the first row and the first column. So the observed value at the first row and first column is 50 and the expected value is 46.703. We square the deviation divided by the expected frequency and we get our first scaled squared deviation term, which is 0.233. Similarly, we calculate 8 more such scaled squared deviation term. We add all of them and we get our test statistic. So this is the table for scaled squared deviation for each cell. So this is the term that we have calculated and we have 8 more such scaled squared deviation term. If we add all the terms, we get our test statistic to be 32.08025. Now we compare this test statistic with the critical value. So to compute the critical value, we need 3 things. We need to know what distribution does the test statistic follow. In this case, our test statistic follow a chi-squared distribution. So we have to look at the chi-squared distribution table. Then we need to know what degrees of freedom to use. In this case, the degree of freedom is number of row, which is 3 minus 1, multiplied by number of column minus 1. So the degree of freedom is 4. And suppose the level of significance specified is 5%. Now based on this 3 information, let us find out the critical value. And if you remember that this is a right-tailed test. So suppose this is the critical value. If the test statistic lie to the right of it, then we reject the null hypothesis. But if it lies to the left of this, we accept the null hypothesis. So this is the chi-squared distribution table. And against 4 degree of freedom, because this is a right-tailed test, we have 5% of the observation to the right of our critical value. So against 5% probability in right tail and against the 4 degree of freedom, the critical value comes out to be 9.488. So the critical value is 9.488 and the test statistic we calculated is way above the critical value. Our test statistic was 2.08025. So we reject the null hypothesis and conclude that the 2 variables, the size and the investment type, they are not independent of each other. They are dependent on each other. So this is how you conduct the test of independence between 2 variables when the variables are categorical or discrete. Although the chance of getting tested on the calculation is very low, but still you need to have a basic understanding of how do we compute the test of independence. And even if you get the question on your exam, most likely you will be provided directly with the scaled squared deviation table and you add all the terms, you compute the test statistic and you compare it with the critical value. If you have time, then I would suggest you to solve through this example where the test statistic comes out to be 35.7415 and with a degree of freedom of 4 and a 5% level of significance. The critical value is 9.488. So we reject the null hypothesis and we conclude that the two variables are not independent of each other. They are dependent on each other. You can also solve through this example where you are directly given the critical value. So the computed test statistic equals to 46.3223. So again here we reject the null hypothesis and conclude that the two variables are dependent on each other.